Swayam Prabha. Digital India. Educated India.
Dear students, welcome to our next discussion on LP duality and sensitivity analysis. In this lecture, we will recap certain concepts of linear programming and simplex method that we have learnt earlier, and we will make a case to motivate why we would need duality. Then we would discuss the formulation and intuition behind duality. And then we will continue our discussions on few advanced concepts like weak and strong duality, complementary slackness, how it is used in sensitivity analysis, and conclude our discussions with an example on infrastructures related to water, power, etc. So, here is a quick recap of linear programming and simplex method. If you recall, we were dealing with the problems of either maximization type or minimization type, which were subjected to certain constraints which were typically listed in the form of less than equal to form. And here A is the matrix of coefficients, X is the vector of decision variables, and B is the constant, or sometimes in linear programming world we also say the resources that are available, that is encapsulated in B. When we learnt about simplex method, we learnt that it traverses from one extreme point to another point, and all these traversing happens through one feasible solution to another feasible solution, and we call these solutions as basic feasible solutions. Since this traversing is happening on the extreme points of a convex region, it is guaranteed that whatever optimal we will get, it is going to be the global optimal for the problem, and that is where the strength of linear programming problem lies. So, despite all this, we need to see that why this duality arises, what is its interpretation, and how it provides a deeper insight into our problems of optimization. So, I have put together some very simple worded discussions on duality before we go into mathematics. So, one broader view of this primal versus dual problem in optimization, operational research and infrastructure management is that of an engineering view or an economist view. So, when we were talking about problems of type, that is maximize profit or minimize expenses, when it is subjected to certain constraints, we were talking about how to allocate limited resources to achieve my goal of maximization of minimization. That is why I mentioned that when we write our constraints in the form Ax less than equal to B, that B is an indicator of what are the limited resources that are available with me. Now, when we talk about dual formulation, we ask a question in slightly different manner. The question here becomes that if I have initial resource as B, let us say that we are talking about total amount of money that is available, and so I would say that A1 x1 plus A2 x2 is equal to B, and B is the money that is available. To produce 1 unit of x1, I would need A1 expense. To produce 1 unit of x2, I need A2 expense. So, A1 x1 plus A2 x2 should be less than equal to B in our linear programming setup. Now, money also has a cost in market. So, for example, if I need to acquire an additional unit of capital, I may need to go to the bank, and bank will give me that money at certain interest rate. So, this money also does not come for free. So, duality exactly helps us understand that problem, that if I have to acquire one additional, be its cost, be its cost. And of course, I would like to minimize the cost that I am going to pay for that additional unit of resource that I am acquiring. And this additional unit of cost, later on we will call it as a shadow price. More formally speaking, this duality asks the question that how do I price each constraint so that the total cost or expenditure in acquisition of these resources is minimized. So, we can say that while LP constraints have an engineering interpretation, we also can see the same LP constraints as economic interpretations through the term called as shadow price that we just introduced. So, let us look into a very simple example to gain more clarity on what we just discussed. Let us say that we have a very simple constraint that x1 plus x2 is less than equal to 10, and here we are simply saying that we can use up to 10 units of this resource efficiently if we have, because this could be x1 is the amount of water that we are withdrawing from region A, x2 is amount of water that we are withdrawing from region B, and there is a resource limit that we cannot withdraw more than 10 units of water if I talk in the infrastructure world. So, x1 plus x2 is less than equal to 10. Now, in primal mindset, it is very clear that this constraint says that sum total of water withdrawal from these two locations cannot exceed 10. So, there is a resource limit on water that is available. Now, dual mindset says that each unit is worth some price lambda. That means, if instead of 10, I want to now buy the 11th unit of water, how much extra I have to pay without resulting in loss of my profit. So, sometimes we also call these as zero sum games. When we will talk about strong duality, this will become even more clearer, but all I am saying is that if this resource limit has to go up by 1, what is the shadow price encapsulated in lambda that is associated with acquisition of that one additional unit. And this example does not only apply to water systems. These kind of examples exist in water, power, budget limits. Wherever we are optimizing something, we would always have changes in constraint, or we may want to relax certain constraints to increase our profits, and that is where discussion of duality or economic viewpoint discussions come into picture. So, again, to concretize it, let us look into a real world duality story, that there is a city that must purchase water from different sources to meet daily demand. However, each source has some maximum capacity. That is, there is a city, let us say that this city here is Ahmedabad. City is of course non-fictional, but the story here is fictional, that it has to withdraw water from two reservoirs, reservoir A and reservoir B. Now, the problem is that reservoir A is located somewhere and it says that I can only give you x1 amount of water, reservoir B says that I can only give you x2 amount of water, and Ahmedabad would of course want to make sure that all the demands are met. So, sum total of x1 and x2 should be greater than certain threshold, but x1 and x2 are individually constrained by the maximum release limits. Now, primal question is very simple, that is how much water do we buy from each source to minimize the total cost or maximize some objective. Minimize the cost is one objective, maximizing the overall water demand being met could be another objective, or so on. But this is how we engineers typically think about optimization problem: maximize profit, minimize losses subject to certain constraints. So, what we do here is that instead of just dealing with primal perspective, we also develop this dual perspective, where we say that each source sets a price for its capacity. Now, instead of maximizing the total profits, city takes an dual or alternate view at the problem, where it says that we will try to minimize the total payments while satisfying the demand. And lambda I is the cost per unit of water that it allocates to source I. Now, in a zero sum game, we do not want our city to get richer by buying the water at lower cost and selling at higher costs, because then the supplier will say that, hey, this is a good product, why we would want you to make profit out of that. So, what city and supplier may want to achieve is that they would like to stay in an equilibrium. That is, city's maximum willingness to pay should be equal to supplier's maximum return. So, supplier is not making money by selling water to the city, and city is not making money by selling the seller's water to the third party, and so on. So, when this condition is met, that is the optimal solution that we obtain from primal is exactly equal to the optimal solution obtained from the dual, because at the end we are going to measure our answers in terms of what is the value of the objective function, or what is the net revenue or net losses a particular agency is incurring. If answer from prior calculation from the primal calculations and dual calculations are exactly same, we would say that strong duality holds, or solution from both sides yield the same optimal value. Now, this strong duality becomes even more powerful when we are talking about linear programming problems, because in linear programming problems, if the feasible bounded solution does exist, the primal solution is equal to the dual solution, indicating the strong duality that exists in the linear programming problem. So, now let us look into this duality's big picture. So, the reason I am iterating it again and again is that, as an engineer, we would get easily familiarized with the primal objective functions, primal simplex methods, etc. But when we talk about infrastructure systems planning and management, we have to be mindful of the economic side of things, and that is where this emphasis on duality becomes very important. So, in primal, we will work on original resource allocation problem, maximization or minimization, whereas in dual we will assign a price to each constraint, and in infrastructure context we would call this extra price as a shadow price. And what we would do is that we would solve primal, dual, and if it is a strong duality problem, answer is going to be same side, and each side would inform what is the resource usage versus resource value. So, if we understand these two words, that what is usage and what is value, this is exactly the difference between primal and dual world. So, now let us look into the mathematical aspect, that how we would change our primal problem to dual problem and so on. So, if you recall that in primal world we listed our problems as maximize C1x1 plus C2x2 plus C3x3 and so on. It was subject to certain constraint. a11 x1 plus a12 x2 plus a13 x3 less than equal to b1. Let us say that this is money constraint. Similarly, we have some human resource constraint. Let us write it as manpower. We say that it is a21 x1 plus a22 x2 plus a23 x3 less than equal to b2, and we can have other constraints and so on. Some constraints may also be greater than equal to, but we would not worry about special cases as of now. And there is one feasibility constraint, that all values of x should be greater than equal to 0, or no negative solutions are acceptable when we are going the simplex route. Now, if we have to write the dual form, we will see that this maximization becomes the minimization problem. The reason is, in maximization we were saying that, hey, let us maximize the profit, and in this case we can always convert minimization problem to maximization problem by multiplying objective function by minus and vice versa. So, we would not worry about this maximization to minimization here, but what is more interesting here is to draw the contrast between the primal form and the dual form. So, if primal objective function is of maximum type, the dual's objective function would be of minimum type. And here we are talking about the shadow price associated with each resource, and as I discussed earlier, that B encapsulates the information about the resource. So, this B becomes now part of the objective function, and we say that minimize lambda 1 B1 plus lambda 2 B2 plus lambda 3 B3 and so on, and here B1 is known to us from the primal system that was given to us, and lambdas are the shadow prices that become our decision variable now. So, when we list this particular problem, it makes sense that why maximization problem is becoming minimization problem, because we would like to pay as minimum amount as possible for each resource that we have to acquire additionally, and this word additionally is encapsulated in the shadow prices that we are talking about. So, each primal constraint has a dual variable lambda. So, if it is a 6 constraint problem, we are going to have 6 decision variables into our dual objective function. Now, you can also see one advantage of writing primal into dual, that let us say that we have our original objective function in primal form which has 8 variables and 3 constraints. Now, the moment we go from 8 variables, 3 constraints, if we go to the dual form, we are going to have our objective function where decision variables are going to be only 3, each corresponding to one of these constraints. So, now you would have lesser decision variables to solve, but of course more constraints to deal with. On the other hand, if you have more constraints and lesser number of decision variables, in that case what will happen is that your constraints in dual form would be lesser in number, whereas the objective function is going to have more number of decision variables. But in case of strong duality, you either go primal route or dual route, which one is easier to solve, compute mathematically, you would have the exactly same answer. Now, let us try to look into one very specific example that how we can easily go from the primal form to the dual form. So, here the problem that has been given to us is the maximization problem, maximize z equal to 3x1 plus 2x2, and it is subjected to constraints 2x1 plus x2 less than equal to 8, x1 plus 3x2 less than equal to 9. when I am talking about these equations in an infrastructure course, I will rather see them with a lens of resources. Again, I would say that, let us say that this is the material constraint and this is human resource constraint. So, if I read it in words, it says that each unit of x1 takes 2 units of material and each unit of x2 takes 1 unit of material, and the total material that is available with me is only 8. Similarly, each unit of x1 takes 1 unit of human resource, each unit of x2 takes 3 units of human resource. Total human resource that is available with me is 9. That is why x1 plus 3x2 is less than equal to 9. And of course, I have to have a non-negative production. So, x1 and x2 they have to be greater than equal to 0. Selling each unit of x1 gives me 3 units profit. Selling each unit of x2 gives me 2 units of profit. I want to produce as much of x1 as much of x2 and maximize 3x1 plus 2x2, that is my total profit. Now, in the dual form, as we discussed, this becomes B1, this becomes B2. It was originally a maximization problem. We will go to minimization problem W, and W will become 8 lambda 1 plus 9 lambda 2, 8 corresponding to B1, lambda 1 be its shadow price, 9 corresponding to B2, lambda 2 be its shadow price. And if we talk about the constraints, we would want to make sure that the shadow prices of each of this from these two constraints, 2 multiplied by lambda 1 plus 1 multiplied by lambda 2 should be greater than equal to the 3 which was the per unit cost that I am cost or revenue that I am getting by selling 1 unit of x1. Similarly, lambda 1 plus 3 lambda 2 should be greater than equal to 2, and these lambda 1 and lambda 2 should be greater than equal to 0. Now that it is clear to us how we go from one objective function to another objective function, let us spend some more time on the constraints themselves. So, sometimes it gets very confusing when we go from primal to dual. So, I will give a very simple example that would make us understand what happens in this primal and dual world. I will take an example of a kid and a parent in this case. So, let us say that there is a kid who wants to make some cupcakes, and he wants to sell those cupcakes in their school fair. It is a very simple setup. So, for each cupcake they are saying that we would charge the profit of 3x1 if it is a chocolate cupcake and 2x2 if it is a vanilla cupcake, and they would want to maximize the profit. So, this is chocolate and this is vanilla, and there are certain ingredient constraints that are involved, because of course kid would want to make infinite cupcakes of using chocolate and vanilla. However, that is practically not feasible. So, there is a constraint that each unit of chocolate cupcake would require 2 units of chocolate and 1 unit of vanilla, and it should be less than 8. On the other hand, vanilla cupcake would require 1 unit of chocolate, 3 units of vanilla, less than equal to 9, and of course kid would want to make number of cupcakes of both types to be greater than or equal to 0. So, from kid side this is a primal problem. Now, if you see, this story exactly gives us the equations that we just saw. Now, let us see that how it would look like from the parents side. Now, parents of course would want to make sure that the ingredients that are given to the kid has certain shadow price associated with them. So what parents would want to do is that they would say that if the kid needs 1 unit of chocolate, they need to pay the y1 amount, or for consistency some lambda 1 amount, and for each unit of vanilla they have to pay, the kid has to pay lambda 2 amounts, because parents would not want that all the ingredients go to the kid for free, and of course kid would want to maximize the profit, but kids and parents would want to set this up as a zero sum game, that is neither parents are losing the money and nor the kid is making money out of this quote unquote business that's going on here. So what parent would do, that they would say that we would sell each unit of these raw ingredients at reasonable shadow price of lambda 1 and lambda 2. They would want to minimize this particular cost so that the buy up of these raw material is feasible, and that is where dual feasibility would also come into picture. On the other hand, they would want to make sure that these raw materials are not priced exorbitantly high, that it does not even make sense for them to be raw material into the final product, which in this case is cupcake. So if you recall here, each unit of chocolate cupcake is fetching 3 units to the kid. So if we say that chocolate cupcake takes 2 unit of chocolate, each cupcake takes 2 unit of chocolate, so 2 lambda 1, because lambda 1 is the shadow price associated with the chocolate, the raw material itself, multiplied by 2 plus lambda 2, that is the units of chocolate, the units of vanilla that will go into the chocolate cupcake, which in this case is 1. It should be greater than equal to the profit or money that the kid is going to make by selling 1 unit of that chocolate cupcake, or 2 lambda 1 plus lambda 2 should be greater than equal to 3. So if you see, what has happened here is that this 2 and 1 becomes part of the first row or first constraint, which is greater than equal to the 3 or the coefficient of the objective function itself. Now similarly we can write that for the second resource, which in this case is raw material vanilla, lambda 1 plus 3 lambda 2 should be greater than equal to 2, and lambda 1 and lambda 2 should be greater than equal to 0. Now if you see that from the kid's perspective, the problem was of primal nature. From the parents' perspective, the problem was of dual nature. Now this kid and parent can be replaced by the reservoir and the dam, by reservoir and the city, Ahmedabad and the 2 reservoir story that we just heard before going to this particular example. But the biggest key takeaway is that these primal and dual are ways to convey the same story from 2 different perspectives. One perspective become an engineering perspective and second perspective become an economics perspective, so that nobody is making exorbitant money at the expense of others' resources. That is what this primal and dual problems ensure. In case of strong duality, this essentially becomes the zero sum game, that is, doesn't matter from which side you are solving the problem, at the end the final answers of both objective functions are going to be exactly similar. But the key takeaway here is that in case of primal to dual, coefficients flip the roles between the primal and dual world, as we saw. You also saw that maximization became minimization, less than equal to became greater than equal to, all the b's became part of the objective function, and all the coefficients of objective function became part of the constraints. And if we understand these three transitions that are happening from primal to dual and the two perspectives that are happening here, it would be much easier to put this duality and primal relationships to use. Now, we have been talking about this word called as strong duality for a while, that it does not matter from which side you solve the problem. If the final answer of your objective function is same in the primal world and dual world, we say that strong duality holds. On the other hand, if the answer of primal is less than equal to answer of dual, this is original objective function in the primal world, this was the original objective function in dual world. So, this was dual objective function. You notice one thing here, I will of course not go into much details about that. The value of dual objective function is always greater than equal to primal objective function, even if this was a minimal problem, if it was the problem of minimization, even in that case this is always greater than equal to the primal objective function. And when this equality holds, the weak duality becomes the strong duality, and as a consequence of this strong duality, does not matter from where we solve, we share the same optimal. And one of the links to the infrastructure world is that in infrastructure systems, we are not only interested in just maximizing the profit, but also interested in determining the sensitivities of our solution, that if one additional resource is acquired from somewhere, how it is going to cost us and what should be the ideal cost of acquisition of that additional resource in our optimization world. Before we go into details of sensitivity analysis, I think this is good time to talk about something called as complementary slackness. If you recall, when we were learning about Lagrange multipliers, we learnt something of this form and sorts, where lambda was our Lagrange multiplier and b minus ax was our constraint, and we called this lambda multiplied by ax minus b equal to 0 as complementary slackness. That is, whenever we were dealing with less than equal to, and this was particularly true when ax minus b was an inequality constraint equation. So, what we learned here is that for this to be equal to 0, either lambda has to be 0 or ax minus b has to be 0. So, when lambda is equal to 0, in that case, we would say that ax minus b can be less than 0 or constraint is not active at the boundary. However, when lambda was not equal to 0, we learned that in that case this constraint was a binding constraint, that it is because of this particular constraint we cannot further maximize or minimize the problem, because solution lies at the boundary of that particular constraint. Now, I deliberately use the notation of lambda throughout our discussion of duality, because this lambda is exactly the same lambda we encountered into Lagrange multipliers, where lambda there was also indicating the cost of relaxation of each constraint by one unit, what would be its impact on the objective function. And we also did lot of sensitivity analysis when we were dealing with Lagrange multiplier. So, the same rationale applies here, that even in case of duality, the original constraint multiplied by its lambda should be equal to 0. And what it tells us, that if a primal constraint is not tight, its dual variable is 0. In simple words, if ax minus b is less than 0, lambda has to be equal to 0 for complementary slackness to hold true. On the other hand, if duality constraint isn't tight, because whatever complementary slackness applies to the dual world, same discussion also applies to the primal world. That is, x multiplied by dual constraint minus c is also equal to 0, because we have been emphasizing that these primal and dual are not written disjointly. Primal informs dual, dual informs primal and vice versa. So, whatever properties apply to the primal world also applies to the dual world, but with the changes in coefficients. Why this complementary slackness is important in the context of infrastructure systems? Because it tells us that if lambda is equal to 0, this constraint is no longer binding. So, I would not want to buy an extra unit of that resource, because even in original problem I am not able to fully utilize that particular resource. So, why I have to pay an additional cost or additional price to acquire a resource that I am not using anyways. So, this lambda equal to 0 indicates exactly that, because we were calling this lambda as shadow price. So, in our cupcake and chocolate example, this could be a third ingredient that kid does not want to use in the cupcake. So, why we would like to pay for that acquisition of that raw material as a parent, because there is no buyer for that, as a result of which shadow price of that third ingredient has to be 0 for this complementary slackness to be satisfied. And if this lambda is very high, that indicates that the cost of acquisition of that particular raw material is also very high if I want to expand on our production capacities, because that resource is the binding, as because its lambda is now active, and if lambda is active, then we have to make a comparison that which particular resource we would like to buy to enhance our objective function in the primal world. So, one word that we always encounter when we talk about this is the shadow price, which is dual variable for the constraint or our lambdas, and it is nothing but the worth of relaxing that constraint by 1 unit, and this is the essence of entire method on duality. One example that we have been talking about is that if water capacity is tight, lambda is the cost benefit of 1 more unit. When we say that it is tight, that means the constraint around water capacity is binding. That means lambda is not equal to 0, and then that lambda, when it is not equal to 0, indicates the cost of 1 more unit of getting that particular acquisition. Now, this also relates to our discussions on resilience in a way that if any commodity has high shadow prices, these constraints are the critical pinch points in decision making. That is, you want to acquire certain material, but its shadow price is so high that you are not able to buy it and invest into your infrastructure planning management. So, we would either find an alternate technology, alternate intervention, because that pinch point is holding us back. It could be technological, manpower, or any other pinch point, but this entire concept of duality does help us in identification of these pinch points, because these constraints would be typically associated with high lambdas or high shadow costs in these systems. And when we talk about this sensitivity analysis, this lambda also tells us that to what particular change in B this system is most sensitive. So, higher lambdas also indicates systems higher sensitivity to that particular constraint. It also tells us that how robust is our solution under various parameter fluctuations. So, if lambda is very low, that also means that if a particular resource changes or fluctuates in the value, it is not going to have a significant impact on our objective function. And you can understand in real world, these objective function and constraints are not written in stone. There is always some errors. It could be measurement errors, or it could be estimation errors that are part of these objective functions and constraint, but we would like our solutions to be robust, because these solutions will ultimately translate to decisions, and decision is going to have the capital cost. So, because of this capital associated with the decisions, we would also worry about robustness of our decisions, which lambda gives insights into. We will talk about that how C becomes part of decision making when we go to the concept of dual simplex in our subsequent lecture, but this also helps us understand this primal to dual form, that what is the allowable increase or decrease in particular CIs. Remember, this CIs was part of the primal objective function. Now, primal objective function themselves do not impact the feasibility of primal solution, but when we take it to the dual form, the primal objective function coefficients become part of the constraints in the duality itself, and that is where feasibility revolves around these coefficients Ci. So, duality also tells us that how much we can change profit per unit of production of different type of commodities without driving our problem into infeasibility. So, that is where this allowable increase or decrease comes into picture. We have already touched upon this in our earlier discussions as well as here, that this lambda indicates to sensitivity as well as shadow prices, and lambda is the bridge between this sensitivity and shadow prices. Again, a very simple example is that if city demand rises from 10 to 11, how does the cost or feasibility of the solution shifts, and higher lambdas are critical constraint to address for the resilience. So, just to sum it up, here is one final example, that if we are dealing with the problem of minimization 2x1 plus 3x2 subject to x1 plus x2 greater than equal to 10, x1 less than 6, x2 less than 8, x1 x2 greater than equal to 0. We may have one observation here, is that surplus variable might appear here, because this is a greater than equal to constraint, but we will not worry about that. We can always write this in a standard form as minimization 2x2 plus 3x2 subject to x1 plus x2. If I multiply both sides by minus, it becomes minus 10, x1 less than equal to 6, x2 less than equal to 8, x1 and x2 greater than equal to 0. I can now easily convert this into a dual form, where I have minimization problem will become a maximization problem of form minus 10 lambda 1 plus 6 lambda 2 plus 8 lambda 3. So, this is my dual objective function. One very quick thing you might have noticed here is that when I listed this problem in the form minus x1 minus x2 less than equal to minus 10, prima facie this was primal infeasible form. The moment I shifted this minus 10 to the objective function itself, I am looking at a dual feasible form. So, even if you have a primal infeasibility, your dual might be feasible and you can continue your iterations from there. And the steps to solve these dual problems remain exactly similar, not even similar, exactly same that what we discussed in simplex tableaus, because you are essentially dealing with same system of linear programming problem. So, all the math transformations that we learnt would apply directly to these kind of problems. In our subsequent discussion, we are going to talk in detail about dual simplex and relate it to the sensitivity analysis of our systems that we have been talking here. Thank you.